Okay. Let's solve the question here. When you want to find Fourier transform the differentiation of a function, where the formula that we use that if you want to differentiate function for n time, then Fourier transform of this, first you have to find Fourier transform of the original function and then multiply it by j omega power n. In this case, you want to differentiate on time. So n equal 1. So the answer would be equal to j omega times this one. That's the answer. Done. All right. Okay. The rule said that when you want to differentiate a function n times with respect to time and then find Fourier transform, all what's supposed to do, step 1, find Fourier transform for the original function before differentiation, which will be x of omega, and I give it to you, not to exhaust yourself. Then you multiply it by j omega raised to the power of n, because they differentiate n times. In this example or this quiz, I asked to differentiate 1 time, so n is equal to 1. So be j omega raised to power 1. It means j omega. So multiply x omega by j omega.
So
that's that.
It was taking the derivative of the lower function and multiplying the derivative.
Just, okay. You have a function without differentiation, and you know Fourier transform for this one is equal x of omega. So if you differentiate this one time, you multiply it by j omega. You differentiate it twice, you multiply it by j omega squared, and so on. I ask only for 1 time. So you multiply by j omega. X of omega is given. That's it. Is it hard? It's just, if you review the lecture, the examples, the thing that you look for the formula, even if you didn't study, you look at the sheet of the formula, find just j omega power n times x of omega. You got to practice a lot about how to use the table of properties. It's actually very simple and very easy, but you got to understand. That's all. How to apply. I'm going to give today 2 extra properties, and then we're done. It does not mean I explain all properties. No. Because it's very silly. Just applying whatever the formula that we have. But I'm training you how to use it. But then you should be able to use all properties of Fourier transform on the table. I'm going to tell you what you are going to discard. Don't look at it. All right. It's not in our interest in this course. But most of the table, it will be, easy for you to apply. And I will write notes about that. So what about if you want to integrate? That's why I start the quiz. You differentiate, you multiply it by j omega power n. What about if you integrate? That would be the rule for integration. Okay. So if you have a function or a signal x of t, Fourier transform for this one x of omega. If you want to integrate it 1 time, and then you want to find Fourier transform, that's f, like script. So you will divide, instead of multiplying, you will divide by 1 over j omega. Till that is just, it makes sense, like, because when you differentiate, you multiply by j omega, and when you integrate, you divide by 1 j omega. And then you add this term, that's the extra term you're going to add for integration to make up for the initial condition of integration. That will be times pi x 0 d omega delta. Let me take one example. Like the same example you did. If x of omega is equal to 1 over 2 plus j omega. Do you know what's the original function of this one? Do you know how to get it? Yeah, exactly. It's actually, it's e to the power of minus 2t ut. That's right. Oh, I got that from the table. Fourier transform pairs. You got to practice a lot of doing that. Don't think just tell me understand now, you'll be fine. No, you got to do by your hand. All right. Now I want the integration of x of t. I can write like that, fine. That's another way to ask. The integration of e minus 2t ut dt. I want to find Fourier transform of this function. So it's the same thing. So what I'm going to do, I'm going to apply this one. I'm going to divide x of omega by j omega. So I have 1 over j omega multiplied by 1 over 2 plus j omega plus pi x capital. It means x of omega when omega is equal 0. You have here x of omega. If you put omega is equal 0, so you'll have 1/2 times delta omega. It's a impulse at omega equals 0. That would be the answer. You can, of course, if you like, I mean, simplify it more. You can multiply. Let me work out and give you the final answer, because when you have this test, I'm not going to leave it like that. I'm going to simplify it and put the final answer Q1. So that will be multiply 1 times 1 is equal 1. J omega times 2 is equal J2 omega minus J times J is equal -1 omega square plus pi over 2 delta omega. That would be the answer. And if you like to put the integer first here, we'll take 1 over omega is a common factor and take minus here common factor. So we have omega minus J2 plus pi over 2 delta omega. That will be the final answer after simplification. All right. Oh, I got one. I just take omega as a common factor, negative omega actually as a common factor. That's negative omega. And then what's left here, omega, and here J2.
How did you get negative omega squared? Where did it be?
Oh, are you talking about this one? Because I multiplied j omega by j omega. J omega times j omega, j square omega square, and j square is equal -1. Yeah, it's okay. You guys don't leave anything. If something that you're not sure in the world, just ask me. It's not a big deal. Okay? Because when I have the exam, you'll have many, and I put multiple choice, and I put multiple choice. Like, I mean, you forget negative here, you forget what's the, I'm so nasty in that. So I mean, you have to be careful. You do it, work it really nicely. Be careful to make sure that you have the right answer. So that's one property. It's very important, and it's used in circuits. It's used in communication, control, a lot of application. Okay. There are two properties left I want to talk about. There's one very important. It's in the exam. I want to read about the exam. It's in the exam because it's very useful. It's called duality property. Yeah. We give you one simple example. Yeah. Pardon me? Duality. Yeah, it's a dual function. Yeah. If you have, that's very interesting. If you have x of t and you find Fourier transform dx of omega. Example. Let's say x of t equal to the same thing, e power minus 2t ut. So what's Fourier transform? Using the table, we'll have 1 over 2 plus j omega. That's good. Now you can, the question will be like, you look at it, you'll think it's really difficult, like, but it's not difficult at all. Find Fourier transform of this function, 1 over 2 plus jt. Because when you find Fourier transform, you find it for signal of function of time, right? So now I'm asking you, find Fourier transform of 1 over 2 plus jt. If you go to the table, you'll not find. If you do integration, that would be, I mean, imagine if you are integrating, multiplying 1 over 2 plus jt times e power minus j omega t, integration with this t. It's not, it doesn't mean it's not solvable. No, it is solvable. I mean, you got to convert 1 over 2 plus jt to magnitude multiplied by e power j something. And then you multiply, let me show you what that. But I'm not going to do it. I can do that easily, but I'll show you what's supposed to be done since it's not in the table. If it's not in the table, you will do the normal thing. This function you multiply it by e minus j omega t dt and you integrate. So how you do that? You got to convert this to polar form, magnitude and angle. So it'll say 1 over 2 square will be 4 plus t squared square root. And then the angle here will be like 10 minus 1, the image t over 2 times e minus j omega t dt. How you express this one? You can make it like 1 over 4 plus t square e to the power minus j theta, where theta is equal to 10 minus 1 t over 2 e multiplied by e minus j omega t dt, and then you integrate. Enjoy your time. I will never like to do that. I mean, of course, there are tables for integration. You can look at it and you get the table and do it, but I mean, it's like, it will take time. Well, how I do that? Using the property of duality. Let me show you how I'll do that. The property just said, if you want to find Fourier transform of function exactly the same in omega, but instead of omega, you put the time. You replace omega by t. That will tell you, you will go back to the same original one. What does it mean? You get x, the small one, function of time, but replace t by minus omega and multiply it by 2 pi. What does it mean? Doing the example, that will make it clear. I'm asking for finding Fourier transform for 1 over 2 plus jt. What is the relationship between 1 over 2 plus jt and 1 over 2 plus j omega? They are the same. I just replace omega by t. That's the duality I'm talking about. So I said, if you do that, you go back to the original signal, wasn't time, and replace t by minus omega. And then multiply by 2 pi. Because when you do the inverse, you have 1 over 2 pi. So, well, how I do that? Well, I will say equal 2 pi. What's x small? It means x function of time. This is my x function of time. So I have e. Write it t like that. Then you replace every t by minus omega. So I will replace this t by minus omega. Oh, that's not good. Minus omega. And I replace the other t minus omega. So the final answer would be 2 pi e to the power 2 omega u minus omega. Save a lot of time. That's the duality. So if you want to find Fourier transform of function, it looks like Fourier transform other function, just get the original one and replace t by minus omega and multiply by 2pi. Nice, right? Easy. Did you look at the integration? If you do integration, it takes a long time. This one just take 1 second. Okay. The last property I'm going to talk about, convolution. Yes. Go ahead. Yeah. It's 2 pi times e. Yes.
How do you get the 2 pi, or is that just because of value?
Oh, I think for 2 pi.
How did you get 2 pi, or is that a given value?
No, it's given. No. 2 pi. It's the formula. Look at the formula.
Okay.
It's equal 2 pi times x. And there is reason for that. There is proof, because when you look for the formula of finding the inverse, you'll find it's 1 over 2 pi integration of. If you look at, so when you go the backwards, so you multiply by 2 pi to get the difference. Yeah, there is reason for that, but it's there in the form. I didn't add it. Yeah. Anything like that, it has to have 2 pi times x of minus omega, x small. You have to be careful when you get x small, it means that was x function of time. And I replace it by t by minus omega. X capital means that was Fourier transform. Very important to observe that. Well, the last thing I want to talk about, the last property that's important, that's called convolution. Convolution, you know that we did convolution before. There are 2 types of convolution. We did one with discrete, and that was very nice and easy and simple. We show 3 methods. But doing convolution by integration was kind of not tricky, but you have to be patient because you are moving something inside, see what the common area, and you do, if you remember the stuff, it's in the exam. So please review this one. Well, what about if you apply Fourier? It will make the continuous time convolution much easier. And actually, we don't use what I show you how you do it, but this is the original convolution. Now I use Laplace or I use Fourier transform, and I will show you now why. If you remember, I mean the headache of the convolution integral. Okay, let me get you a simple example here. Yes, the convolution will write like that. If you have a system, and this system has impulse response h of t, and you have an input, and this input x of t, and has an output y of t, and you wish to find the output, we say that the output will always equal to the convolution of the input on the impulse response. This is like transfer function. It's like related input by output. So you get the output, you convolute the input signal on the impulse response. Okay, and then you do the integration. If you remember, like I think you make integration x of tau, h of t minus tau, d tau, and from 0 to t, and that's where you flip the diagram, and then you move it, and step by step see where the common thing. Well, how we do it with Fourier? So that's very simple. Find Fourier transform of each one. Find Fourier transform of the impulse response. That we'll call h of omega. Of course, we turn it to uppercase letter once you have the Fourier transform. Turn this one to Fourier transform. According to that, y of omega, the output will be equal x of omega times h of omega. That will be the output, just multiply. Yes.
You suppose you want to tau?
Yeah. That's the conclusion, the old definition of convolution. Yeah. And we said that you can flip it. You can say h of tau times x of t minus tau. Both are equal. So now we can get the output response just by multiplying Fourier transform of each. Let's take one example. If we have a system should rest at home. Yeah, you're sick.
Absolutely not.
You can be in Zoom. H of t. That let's say that it's equal to e minus t ut. That's the impulse response. That's the characteristic of the system itself relate the input and output. It looks like that. If you want to sketch it, that's h of t. And let's say you have input, and this input was like that. From 0 to 2, and was equal to 1. That's x of t. The question is, we want to find the output. Well, according to the convolution, we'll say y omega is equal x omega times h omega. So I need to find omega Fourier transform of each. This one, we did it last time. That's the rectangular pulse shifted. If you look at the original one, that's a good, revision for what we did. Like the original rectangular pulse in the formula sheet, it's given like that. Like start from -1 to 1, the height is 1. If we go to the Fourier, always you print the table with you when you are working with that. The rectangular pulse here, yes, that's called in the formula sheet rect t over t capital, and t is the width, and t in this case is equal to. So, and it's given in the table. The answer will be t capital. I will just write the answer: t capital to sinc t capital, which is equal to over 2 pi omega. So you can say it's equal to sinc omega over pi. That's the original rectangular pulse, standard form, symmetric about it. But now when it shifts, it shifts. So what I'm going to do, I'm going to apply the property that we did last lecture when you have shift in time. The same table, you can look for the property. The time shift, yes, time shifting. Time shifting, I tell you that x t minus alpha, it will go the same thing, omega, but just multiplied by e minus j, the delay. Caution. When you have Fourier transform of any function, you should not have any t, because it's not a function of time. Okay? Always an omega, so make sure. So when you choose a multiple choice, if I ask about some Fourier transform of some function, if you find something look right, but there is t, they ignore it, because the Fourier transform function of omega, not t. All right? So that's the way to do it. So what I do here, that's a rectangle pulse, but shifted by 1. I shift by 1 towards the left. So actually, I have a rectangle t minus 1 and the same t, the same width. So I'm going to apply the formula here. The e minus j, it's alpha is equal 1 in this case. So e minus j omega time x of omega. I had it here. That's x omega 2 sinc omega over pi. Okay. So that's the x of omega. So I got 1. Now I want to look for the impulse response h of t. H of t is easy. It's e minus t times the step. And to get the Fourier transform from this is from the table already, not shifted anything. That will be equal 1 over alpha is equal 1 plus j omega. That's it. So I got this and this. So now I want to find the output. The output y of omega is equal to multiply both. So I have e minus j omega times 2 times sinc, that's all multiplication. Sinc omega over pi times h, which is 1 over 1 plus j omega. So if you arrange it, so you have 2 e minus j omega sinc omega over pi divided by 1 plus j omega. That will be the output in frequency. So it's easy. You don't make integration, anything like that. All right. So I'm done with the last property, and I will write you notes what property should review, because I mean the rest will be just something like that. You just apply, and then put some example, solved example. I think I already uploaded some solved example. And there are exercises practice. Try to do. Okay. Just I want to mention something, not property, but something that you take advantage of it. What happens if the function is even or odd? What you can get? Of course, you can simplify it like we did in Fourier Transform. Don't worry, all the things. I mean, if you look at even at the folio, you find everything is published. They're almost there. So what happens when you have a symmetric function? Maybe you have even function, and maybe you have odd function. Even function, it means x of negative t is the same. It's symmetric about the vertical axis. Odd function when x of negative t is equal minus xt. If you have it even, so x of omega will be equal to, you don't have to integrate from minus infinity to infinity now. So you integrate from 0 to infinity, the same function that you did, x of t, but not e to the power minus j. We used to do e minus j omega t dt. First, it's even. So we expect is going to be only the real part, which would be cosine. That's number one. Number two, you make from 0 to infinity. So you make it double, because symmetric. What do you expect for the odd? The x omega will be equal minus j2, the integration from 0 to infinity, x of t multiplied by the sine, omega t dt. So these are the difference between the even and odd. Okay. So we're done with Fourier transform.